something.
Alright, here you go. So we got conditional probability. And we talk about conditional relative frequency, right, with our two-way tables, and this is similar to that, where you're looking under a condition. So if this is true, then what's the probability of this happening? So that's what we're looking at today, conditional probability. This is the conditional probability of B given A. So given that the event A has already occurred. And you see the way that it's listed here. This is important to understand. When you see the parentheses and you see a vertical line in between, we're looking for the probability that B will happen if A has already happened. Okay, the second part is what has already occurred. So we have to do something with that when we go to solve our problems today. So knowing that that second value, the one after the line, has already happened, that limits our outcome, that limits our sample space for this. Because now we're getting rid of all the ones where A didn't happen already. Okay, so we're going to see as we go through a couple different ways of asking this question, what we're going to do with something like that, where A has already occurred. Okay? So that is our conditional probability. So let's look at our first type of problem here. Family has 2 dogs, 2 cats, randomly select a pet to get brushed, and then randomly select a different pet to get a treat. That's a weird setup. I don't know why you would only give a treat to one and only brush one, but that's what we're doing. I don't know. We're playing favorites. Find the probability that they select a cat to get a treat, given that they selected a dog to get brushed. So it's really important to understand the order in which things are happening here, because that's going to change our probabilities here. So they select a pet to get brushed and then select a different pet to get a treat. So we're picking the one that gets brushed first. And notice that it's a different pet, so it can't be the same one. This is like that homework problem we had the other day where it said without replacement. We are not putting that first, the pet that gets brushed back into the group to get a treat. That brushed pet cannot get a treat. Okay, so we want the probability that they select a cat as the second one, given that they selected a dog the first time. So if I wanted to write that out here, that would be the probability that they select a cat to get the treat, given that a dog was brushed, right? Something like that. We can organize it in that manner. So we're trying to say that the second thing has already occurred. We want the probability the first one's going to happen. Now, what the book is going to show, listing out all the possibilities, the whole sample space. I don't like that. I think that's too much. Right? They're writing out the entire sample space here, and then just focusing in on the ones where a dog was picked first. Okay, we could do that, but really we could also just use our logic here. Okay, we know we've got 2 dogs and 2 cats. Well, if the first one I picked was a dog, how many pets do I have left of that I could possibly give a treat to? 3. How many of those are cats? There's our probability. Right? So it's just it's taking that first one away because I know that has happened already. And then it's what's the probability of what's left. That probability is going to change if I change this. Right? If I say now that it was a cat that got brushed, what's the probability that a cat is going to get the treat? That's going to be 1/3. Right? Because now we took the cat away. We still have 3 pets, but now we only have 1 cat, 2 dogs left. Okay? So we have a 1/3 probability. Okay? So that's what we have to keep in mind as we do this. Any questions on that one? Okay. So now let's look at it in terms of a two-way table. Okay, we're asking a couple different things here. It's important to understand what we're looking at in terms of the situation. We have a two-way table. We've got defective and non-defective. and if it passed or failed an inspector check. Tell the person next to you, just for A, what does that mean? What does this mean right here?
What's the probability that a inspector is gonna pass given that the first one was defective? Right?
I think that sounds right.
And then what's the probability that the inspector wait for defective? I'm so confused.
I was gonna
Oh, they're just
fail
words.
again.
All right, what is that first one asking for? What's that first one gonna ask for? Edith? How many would pass if they are defective? Yeah. Yeah. I would word it maybe slightly differently, right? How many would pass? What's the probability that they would pass? Because it's not how many, right? We're not looking for a number, we're looking for a probability. So what's the probability that it's going to pass given that it is defective? So given that it is defective, what's the probability that it's going to pass? So this is that conditional relative frequency. Because now, given that it's defective, we are only looking at that row. So the probability that it's going to pass, given that it's defective, what would that fraction be? 3 out of 39. We're looking at the total, right? There were 39 total that were defective. 3 of them passed. 3 out of 39 or 1 out of 13 would be our probability. Okay. Tell the person next to you what fraction is going to be for that second one.
What's the probability that they fail, given that it's not effective?
461, 11 out of 4.
Yeah.
You might be lost.
All right, so what's our fraction going to be for our second one? For our probability that it fails, given that it is non-defective. There you go. 11 out of 461. Because now we're given that it's non-defective. So now we're only looking at the bottom. And we want the probability that it fails, just given that it's non-defective. 11 out of the total 461. There you go. Okay, so it's just a matter of paying attention to what that second part says, because that's telling us what part of that two-way table we're going to concentrate on. Okay, it's conditional, so we're only looking at one row or one column at a time. All right. Any questions on that? Okay. All right, so really, we got a couple last things here that we got to go over. And this one's probably maybe the trickiest to comprehend right away, just to understand exactly what they're telling us. I want you to write this down. Okay, let's have that in our notes. That's going to help us set up some fractions, set up some problems to be able to solve. I'll give you a second copy of that. We'll talk about what it means. All right, so we know that this symbol represents the probability of B happening given that A has already happened. Okay, we just talked about that. It's given that A has already happened. Another way that we can figure that out is by setting up this fraction, this ratio. And what this is going to be, the top is the probability that both things happen. Right? Probability that we get A and then we get B. So that's the overall probability that that happens. The denominator here is just the probability that A has happened. If you think back to that two-way table, that's what we did. Okay, we had those 4 defective, non-defective, pass, fail. right? The top A and B happening, that was here, that was defective and passed. Divided by the probability that it was defective. That was this, that was that whole probability that A happened. We took that square divided by that square and got it. Okay, so this is what we did. We're just putting, we're just putting it in a different way, right? We've got a fraction now, we've got representation using our probabilities and our parentheses here. Okay. As we move forward though, I'm going to refer back to this because they're not going to give us the two-way tables. They're just going to give us stuff in words. And we got to be able to find these two things to be able to create our fraction. I'm going to have this off to the side so we can refer back to it. Very appetizing school lunch there. How do you-
Metal
There's
silver.
They give
no
us
meat on that
glass.
plate at all. It's rice salad, orange and
It's
apple.
colorful though, that's good.
And a giant actual glass of milk.
Yeah.
Metal silverware that's in it.
Yeah. You guys get like actual glasses to drink out of, right?
Yeah.
Yeah.
They fill it up
And
for
metal
us
forks,
too.
Fill it up all the way. Yeah, metal fork. Yeah,
Plastic chairs,
great.
Plastic, yeah.
Really, really.
Reusable chairs.
All right, so they give us some information here, right? It's not a two-way table, but they give us some percentages here. At a school, 60% of students buy a school lunch, 18% of students buy a dessert, and 10% buy a lunch and a dessert. Now we could create a two-way table. We don't have to here. We want the probability that a student who buys lunch also buys dessert. How would I represent that in terms of like the probability of something and something? I'll just talk to the person next to you. What's going to go where in terms of my two sides here? Talk to someone. What do you
It's
think?
probably
You're
dessert
gonna have
and then
lunch
lunch.
for, yeah, you're gonna, what's the probability they're gonna get dessert after they eat lunch?
Yeah, so probably dessert.
Yeah, like P parentheses.
Yeah.
All right. Hey, remember that second part is the one that we know has happened. It has already happened, right? What has already happened in part A? They buy lunch, right? Who buys a lunch also buys dessert. So we know they bought a lunch. So we're looking for the probability of dessert given lunch is what we're looking for. Okay. Now, if we want dessert given lunch, we're in this situation now. Notice that the denominator is always the probability of that thing that has already occurred. So for this problem, what's the probability that they got lunch? 60%, right? 60% of students buy lunch. So our denominator here is going to be that 60%. On the top is the probability that both things happen. What percent of students got lunch and dessert? Lunch and dessert was 10, right? I don't know where you got 72 from.
You just had it. This is obviously the best.
So again, the bottom is just lunch. The top is both of them. So now we got a 10 out of 60 chance, a 1/6 probability, 16.7%, however you want to represent it. But there's a 1/6 probability that a student who buys lunch also buys dessert. Okay, by using this stuff. Okay, I want you to work together, find that second one. This is different. Find that second one.
What's the probability that a student buys dessert also buys lunch? Okay, so it's just that for flip.
Yeah.
So six or.
So,
Yeah,
because
wait,
it's
no.
18.
Oh, okay, yeah. Oh, yeah. Equals
60 over 18. Also by, oh yeah.
What is the probability student who buys dessert, which is 18, also buys
10, yeah, 10. The total of the, I guess,
buys dessert. Also buys.
it's easier if you write it. Do I want to?
All right, so what is that fraction? Because now we just switched the two parts, right? Now it's given that we got dessert. We want to know what's probability they also buy lunch. What's that fraction going to be here? Part? It's 10 over 18. 10 over 18. Because remember, the denominator is the probability of just that second thing happening. 18% got a dessert. That's the denominator. The top is still both of them happening, which is still 10. 10 out of 18, we would simplify that down 5/9, 55.6%, whatever you want. All right, good deal. Questions on that? And like I said, that's probably the trickiest concept to get, is just being able to set up that fraction correctly. Okay. All right, we got one more thing here to look at. A nice word problem about her running.
So happy. Who's that happy?
Very
when they
happy
run?
runner. I don't know
I would not be that
many runners that are that happy. Not while they're running.
happy. Nah, you can tell she hasn't ran it on. She's not even sweaty.
That was their first step.
Yeah.
Yeah, most likely.
Okay, so I know you can read it. The question is, which of these three routes should she use from now on based on the data? She's got three routes. Sometimes she reaches the goal, sometimes she does not. We want to obviously reach our goal more often than not. So we just want to know which one should we be using. Talk to each other, figure out how are we going to know which route to use.
R, B, and yeah, B. I don't know. I'm just looking at it. Yeah, but I actually have to
So
put
we
it.
probably have to do like
And then see which one is right. So just looking at it, why wouldn't you choose? I'm not even.
I don't know if she likes me though.
This is.
I'm a police.
This is.
maybe we should ask her her opinion.
Yeah.
She reaches for
Which route should we use? B. Why? Okay, I know we can kind of look at that and say, yeah, she probably reaches it more often. How can we know for sure that she reaches it more often? Divide what? Divide like this, divide by this, or what?
Yeah. No,
This divided by this.
no.
Somebody help him
I
out.
don't think he knows.
What are we gonna do? Jacob? Yeah, divided by the total. Divided by the numbers that are out here. Right? Because if you take this number divided by the total, that's gonna give you the percent of time that she reaches her goal.
Oh, yeah.
Right? Take this divided by the total, percent that she reaches the goal. You compare all three, we can see which one does she reach the goal most often, and that's gonna be the one. If we actually end up solving this out, they wanted us to make a two-way table out of that, we don't have to do that. Right, but if we do that, 73.3% of the time, it's gonna be right. Okay, obviously, they're doing more work than we did. You guys were able to just look logically and think about it, but you are doing this. When you're dividing by that total all the way off on the right side, this is what you're doing. You're saying the probability she reaches the goal, given that she ran route B. So route B and reached the goal, divided by the total from route B. All right, that's what we did. We just did it automatically without having to go through that process. Okay. So that is conditional probability. Any questions about our conditional probability? No? All right.